Hello, happy summer. This is Mrs. Riddle. Thank you for taking time to do your summer work. I appreciate it. We are going to be working on chapter 2, which is on limits and continuity. And those chapters are pretty straightforward and hopefully some review from Calc 1. And if we can get this chapter out of the way, we'll be able to start right away with derivatives when we get back in August. And that will free up some time for us in the spring when things get a little bit harder. So anyway, this is about my 5th time trying to make this video. I've messed it up about every time, so let's see if I can get it right this time. So what you're going to need to have is a calculator. So if you don't have your calculator with you, go ahead and pause and grab that calculator so you can practice along with me. We're going to be practicing some calculator skills. And then if you prefer to use guided notes, which I recommend, you also want to have those printed out. You can access the guided notes from Google Classroom. And if you don't prefer to use guided notes, you're welcome to take notes in a notebook. It's really your preference. Okay, so let's get started. So we've got 2 objectives. We're just going to get through the first page of the notes today in this video, and you can work at whatever pace you'd like to work at. You could do a couple in a day or spread them out or cram it all in a few days before school starts. So anyway, we're going to start with the very first page. So if we take a look at this problem, this is the idea of a rock breaking loose from a tall cliff. And we want to know what the average speed would be during the first 2 seconds of the fall. Experiments, and I think those might be experiments regarding gravity, give us that the function y equals 16 times t squared will show us how far the object has dropped. So let's take a look. If we want to know how far the object dropped, we could first of all figure out how far it dropped. So we want to know the average, the average. So what we would want to do is, what would be y of 2? Hold on, that's kind of fat. I don't really like that. Let me get this a little skinnier. So y of 2 subtract y of 0 over 2 minus 0. So if I substitute 2 into t for time, I get 2 squared 4, 4 times 16. $64 divided by 2. Did you guys do that really fast in your head and you were waiting on me? Okay, equals 32 feet per second. So this is going to be the average speed over the first 2 seconds of that free-falling object. To write a general equation, we could do y of b minus y of a divided by b minus a. And that would tell us if we wanted to know between time 6 and 4 or 10 and 5, that could tell us the average speed between any time interval. But the question that maybe is really interesting to some of us is, what would be this speed at exactly 2 seconds? Not over a time period, but at exactly 2 seconds. So we don't really have the tools for that at this point, but what we could do is just to pick something really, really close to 2. So maybe we could do y of 2.0001. That's really close to 2 seconds, right? And we could subtract that from y of 2. And we could divide that by b minus a, 2.0001 minus 2. And if we were to put that into our calculator, I'm going to show you that here in a minute. So I think I'll just start with, let me start with the 84. I'll show you that on the 84. And then I'll show you how to do that on the Inspire. So I worked this problem earlier because, like I said, I've tried this a couple times. So our function is 16x squared. with x representing t as in time. So if I go back to my calculator screen, let me show you how to get to this. First of all, we go alpha y equals, and that gives us a fraction bar, and that fraction bar is really helpful. And I'll show you the fraction bar on the Inspire here in a little bit. But now if I go to vars, y vars, and function, I can evaluate that y1 at any value. So I'm going to type 2.0001, and I'm going to subtract that from vars, y vars, enter, enter, and I want to evaluate that at 2, and divide that by 2.0001 minus 2. So that's how you could enter that into your calculator. So that would be approximately 64 feet per second. So I'll go back here. So I'm going to actually make that approximate. 64 feet per second. Okay, let me show you how to do that on the Inspire. So on the Inspire, on the home screen, we have two modes that your calculator can work in. Scratchpad would just be for like a real quick computation. But Documents is what we're going to want to use more often. The Documents page allows us to save. It's also helpful if you are taking an assessment, you can save the pages. So I'm going to go to 1, and I'm actually going to go number 2, and I'm going to add, let me add a graph. Okay, so let me put 16x squared in there. I'll hit enter. There's my function. Now I'm going to go back to my calculator page. You can also add a page at any time, and it's right up here. I go back to my calculator page. I'm going to make a fraction bar, and that fraction bar is located above the division sign. If I make this a little bigger, would that help? Okay, so now vars is found right here. So I'm going to do vars F1, and I want to evaluate that at 2.0001, and I'm going to subtract that from vars F1 at 2 divided by 2.0001, subtract 2. Okay, so that's how to evaluate those with the 84 and then with the Inspire. And we'll just keep working on our calculator skills throughout the whole course of the year. Okay, so back to our notes. So that is average rate of change. And then we use that average rate of change to get real as close as we could to the instantaneous rate of change. So using this idea of getting really, really close to something, let's talk about limits. An informal definition is a limit describes how the outputs of a function behave as the inputs approach a particular value. So let's apply this. It's important to remember that the limit does not depend on the actual value. It's really the behavior as the function approaches that value. So let's take a look. This here would be read like this: the limit of f of x as x approaches -2. So as the limit approaches, as x approaches -2, if I look at this, if I'm coming from the left-hand side, I'm approaching 1. F of x is equal to 1. And if I'm approaching from the right-hand side, f of x is also equal to 1. So the limit is going to be 1. So using this idea, why don't you take a look at the limit of f of x as x approaches 0 and see what you get. Okay, so from the left-hand side, we're approaching 1 as x equals 0. From the right-hand side, we're approaching 1. So the limit is also equal to 1. Okay, now, so using a graph is one way to find a limit. Another way could be using a table. So first of all, if I substitute 0 into this function, I'm going to get the sine of 0 divided by 0. Well, I know that that's undefined. So I'm going to go to my graph, make a new page. Oh, not geometry. Oh, geez. Okay, so now I'm going to do my fraction bar again. Well, oh, okay, got it. I made an error. Yep. Okay, let me try again. Fraction bar. Now your sine function is going to be where the trig button is. So you're going to do trig, sine. Oh my gosh. Let me try for a third time. Trig. Sine x divided by x. So it looks like f of 0 is equal to 1, but we know that that's not true. So if we go to sketch this graph, I'm going to go back to the notes, and we were to draw this. You know, it looks kind of like this, but really, in reality, there's a hole there. That's a pretty bad drawing, but you get the idea. There's a hole right there. So I think that the limit is going to equal 1. Looks like from the left-hand side, I'm approaching 1. From the right-hand side, I'm approaching 1, even though at 0, sine x over x is undefined. But I could verify that with a table. So what I'm going to do is I'm going to try some values really close to 0. So I might try negative 0.001 and 0.001. I'm going to go back to my calculator. You can use your calculator. Now remember, this is F2, so that's going to be important. I have sine x over x in F2. I'm going to go back to my calculator page. And whoa. I don't know what that is. Let's do escape. Let me make a new page. Kind of having problems with this mouse. Okay, so I'm going to do vars. Now I'm going to select F2. And I want to evaluate that at negative 0.00. Did I do 2 zeros or 3? I think I did 2 zeros. So let's see what that equals. And I get 1. And I'm going to verify on the right-hand side. Remember, my function's in F2. Okay, so based on, oh, look at that, I made a mistake. I did f of 1. So let me try again. So vars f2 0.001. There we go, 1. So I can confirm with my table that the limit is in fact equal to 1. So this equaled 1 and that equaled 1. So therefore the limit as x approaches 0 of sine x over x is equal to 1. So there's a way to find this graphically, and there's a way to find this using a table. Okay, so finally, let's look. The limits described above are two-sided limits. We can look at limits from one side, either the right-hand side or the left-hand side. And how you know is if there's a plus sign right here, then that's going to be from the right. There's a minus sign, that's going to be from the left. So I'm going to do this first one, and then you're going to do the second one. Now, one thing that's important is that the limit from the left has to equal the limit from the right for the limit to exist. So let's take a look. Let's approach -1 as x approaches -1 from the left-hand side. So I'm coming from the left-hand side. My limit is going to equal 0. My limit as I approach -1 from the right-hand side is equal to 1. And f of -1 is actually equal to 1. Okay? So now I would like for you on your own to try this. What's the limit as x approaches 1 from the negative side, from the left-hand side? What about x approaches 1 and make that I think that's a positive in your notes. That's a typo here. Approach 1 from the positive side and then tell me what f of 1 is. So I'll give you a second to figure that out and then we'll compare. Okay, so as f of x approaches 1 from the negative side, my limit is going to equal 1. As I approach 1 from the right-hand side, my limit is actually 2. And f of 1 is actually down here. Do you see that? And that's equal to -2. So that's an example of a left-handed limit, a right-handed limit, and then the value at the point. Okay, so that's what we're going to do. That's it for page 1. And then we'll continue on with these notes in another video. Thank you.